Introduction. What is kinematics? Kinematics is the branch of physics that deals with the motion of objects without considering the forces causing the motion. Example: studying how a car moves from point A to B without worrying about the engine or fuel. What is a particle? A particle, also called a point object, is an object that has no size, only position. Example: a car viewed from a tall building is treated as a particle. Earth in space, when considering orbit, can be considered a particle. Trick: particle is equal to position only, no shape or size. What is rest and motion? Term definition. Example: trick rest. If the position of an object does not change with time relative to its surroundings. Book on a table. Parked car. Rest is equal to re plus still is equal to remains still. Motion: if the position of an object changes with time relative to surroundings. Moving bus. Flying bird. Motion is equal to move plus position. Important note: rest and motion are relative. A person sitting in a moving train is at rest w.r.t the train, but in motion w.r.t the trees outside. Part 2. Types of motion. Motion can be classified into. Enter list. 1. Random motion. 2. Translational motion. 3. Rotational motion. 4. Oscillatory vibratory motion. Exit list. 1. Random motion. Definition: motion in which particles move without any fixed path or direction. Example: dust particles in the air. Movement of gas molecules. Trick: random is equal to roaming without rule. 2. Translational motion. Definition: motion in which every point of the object moves the same distance in the same direction in a given time. 2 types: rectilinear motion along a straight line. Example: car moving on a straight road. Curvilinear motion along a curved path. Example: ball thrown in the air. Trick: translate is equal to shift, recti is equal to straight, curvy is equal to curved. 3. Rotational motion. Definition: when a body moves in a circle around a fixed axis, it is in rotational motion. Example: fan blades rotating, earth rotating on its axis. Trick: rotation is equal to round and round. 4. Oscillatory vibratory motion. Definition: back and forth motion about a fixed position. Example: swing moving pendulum, guitar string vibrating. Trick: oscillate is equal to and fro. Quick summary table: type of motion, path type, key feature. Real life example: random, no fixed path, unpredictable movement, dust in wind. Translational: straight or curved, whole body shifts equally, car moving, bullet fired. Rotational: circular, spins around an axis, wheel. Earth's rotation. Oscillatory vibratory. Back and forth repeats about a mean position. Swing pendulum, tuning fork. Teacher's tip: use classroom objects to demonstrate motion. Pen rolling is equal to translational. Spinner toy is equal to rotational. Ruler vibrating when hit is equal to oscillatory. Ask students to identify motions in daily life. Washing machine. Drum is equal to rotational. Car is equal to translational. Lecture note: scalars, vectors, and distance. Scalars and vectors. What are scalar quantities? Picture 72. A scalar quantity is a physical quantity that is described completely by magnitude, numerical value only. No direction is involved. Examples of scalar quantities: distance, speed. Mass, density, temperature. Trick to remember: scalar is equal to size, magnitude only. What are vector quantities? A vector quantity is a physical quantity that has both. Enter list 1. Magnitude 2. Direction. Exit list. Just knowing the size is not enough, you also need to know where it is pointing. Examples of vector quantities: velocity, acceleration, force, torque. Trick to remember: vector is equal to value plus where, direction, distance. A scalar quantity. Definition: distance is the total length of the actual path traveled by a particle from its initial position to the final position, regardless of direction. It is a scalar quantity. It depends on the path taken. It is always positive or zero. Example explanation based on the diagram. Consider 2 points A and B. A person can go from A to B using. Enter list 1. Path ACDB 2. Path AOB 3. Path AB straight line. Exit list. All three reached the same final point B, but the distance traveled in each case is different because the paths differ in length. This shows that distance is path dependent. Units of distance: SI unit, meter, Cbse unit, centimeter, cm. Quick recap: table concept type depends on direction. Examples: scalar. Magnitude only, path or value no, speed, distance, mass, temp. Vector: magnitude plus direction both yes, velocity, force, acceleration, distance. Scalar: path taken. Number 5. Path walked around a park. Teacher tip: use string to show path on a board to demonstrate how different paths give different distances between same start and end points. Give students 2 to 3 examples and ask them to classify each quantity as scalar or vector. Lecture note: displacement. What is displacement? Displacement is the shortest straight line distance between the initial position and the final position of a moving object, along with its direction. It represents change in position with respect to direction. It is a vector quantity, meaning it has both magnitude and direction. Displacement is path independent. Key points: displacement is the shortest distance between the start and end points. It does not depend on the actual path taken. The direction is important. Represented using arrows or directed line segments. Units of displacement: SI unit, meter, Cbse unit, centimeter, cm. Important concepts. Enter list 1. Displacement is a vector. Example: displacement from A to B, AB, displacement from B to ABA. These are not equal because the direction is different. 2. Magnitude of displacement is equal to length of the shortest line from start to end. Exit list. Example 1 from earlier: distance. Example: let's consider A and B as 2 points. Distance could be along ACDB, along AOB, along AB, shortest. Displacement is equal to line AB with direction from A to B. Even if the path is long, displacement only looks at the initial and final positions, and takes the shortest path between them. Example 2 displacement in two directions. A person walks 3 kilometers towards east from point P to Q, then 4 kilometers towards south from Q to R. Total distance is equal to 3 kilometers plus 4 kilometers is equal to 7 kilometers. Displacement is equal to direct straight line PR. By drawing PR and using scale, the length is equal to 5 kilometers. Hence, the magnitude of displacement is 5 kilometers, and the direction is approximately southeast. Resultant displacement in this case, displacement PQ is 3 kilometers east. Displacement QR is 4 kilometers south. These two are components of the final displacement PR. Displacement PR is found using the Pythagoras theorem. P equals square root of open parent cap P cap Q close parent squared plus open parent cap Q cap R close parent squared. N square root equals square root of 3 squared plus 4 squared. N square root equals square root of 9 plus 16. N square root equals square root of 25 equals 5 kilometer. Picture 71. Tricks to remember displacement is the shortest path. Displacement is a direct deal, shortest and straight. Direction matters. Without direction, displacement is incomplete. Distance is long, displacement is smart. It skips all turns and curves. Quick comparison: distance versus displacement. Feature: distance, displacement type, scalar vector. Path depends on path taken. Shortest path only direction not required. Required value always positive. Can be positive, negative or zero. Example: walking 7 kilometers in zigzag. Straight line from start to end is equal to 5 kilometers. Lecture note: speed and its types. What is speed? Speed is the rate at which an object moves. It tells us how fast something is going without considering direction. Formula: speed equals distance over time. Scalar quantity has only magnitude, not direction. Path-dependent units of speed: SI unit, meter per second, ms or ms superscript 1. Cgs unit, centimeter per second, cms or cms superscript 1. Trick to remember: speed cares how fast, not where. Speed is equal to distance divided by time. Types of speed: 1. Instantaneous speed, speed of an object at a particular instant of time. Think of speedometer in a car. It shows instantaneous speed. Definition: it is the speed measured in a very small time interval, almost zero. 2. Average speed, used when speed is not constant. Average speed equals total distance over total time. If a body covers distances x sub 1, x sub 2, x sub 3 in times t sub 1, t sub 2, t sub 3, then average speed equals numerator x sub 1 plus x sub 2 plus x sub 3 and numerator over denominator t sub 1 plus t sub 2 plus t sub 3 and denominator. Picture 70. Example: if a car travels 10 kilometers in 1 hour, then 20 kilometers in 2 hours. Average speed equals numerator 10 plus 20 and numerator over denominator 1 plus 2 and denominator equals 30 thirds equals 10 km. 3. Uniform speed when an object covers equal distances in equal intervals of time. Example: a clock's second hand moves with uniform speed. Trick: uniform is equal to equal time equal distance. 4. Variable speed. When an object covers unequal distances in equal intervals of time. Example: a plane during takeoff speed increases, mid-air remains constant, and landing speed decreases. Trick: variable is equal to varying speed is equal to uneven motion comparison table. Type of speed definition. Example: formula description: speed, rate of motion, distance, time. Car at 60 km per hour speed is equal to distance divided by time. Instantaneous speed at a particular moment. Speedometer reading snapshot speed. Average speed total distance divided by total time journey with different speeds. Average speed is equal to total distance divided by total time. Uniform speed. Equal distance in equal time. Ceiling fan blade speed is constant. Variable speed unequal distance in equal time. Airplane during flight. Speed changes. Teacher tips: use a stopwatch and measuring tape in school ground to show how to calculate speed. Plot time versus distance graphs to identify uniform or variable speed. Ask students: if your school bus took longer today, did the speed decrease? Lecture note: velocity and types of motion. What is velocity? Velocity is the rate of change of displacement with respect to time. It tells how fast and in which direction an object is moving. Formula: velocity open paren v equals displacement over time equals over t. Velocity is a vector quantity, has both magnitude and direction. Direction of velocity is the same as the direction of displacement. Units of velocity: SI unit, meter per second, ms or ms superscript 1. Cgs unit, centimeter per second, cms or cms superscript 1. Trick to remember: velocity is equal to speed with direction. Velocity is equal to displacement divided by time. Uniform velocity: a body has uniform velocity if it covers equal displacements in equal time intervals. Moves in a straight line, maintains constant speed and direction. Picture 69. Example: a car moving in a straight line at 60 km per hour without changing speed or direction. Trick: uniform velocity is equal to constant speed plus straight path plus same direction. Non-uniform velocity: variable velocity occurs when displacement changes unevenly with time. Speed or direction is changing. Picture 68. Example: a bike that slows down or turns. Uniform and non-uniform motion. Uniform motion: object covers equal distances in equal intervals of time. Speed remains constant. Example: a train moving steadily on a straight track. Non-uniform motion: object covers unequal distances in equal intervals of time. Speed or direction varies. Example: a bus in city traffic, stop and go. Quick recap: table concept, scalar vector path value. Examples: speed. Scalar path based always plus v 60 km per hour without direction. Velocity vectors straight plus v 0 60 km per hour east. Uniform motion equal district time constant fan blade steady train. Non-uniform motion, unequal district time, varies running person, city bus. Common questions teachers can ask. Enter list. 1 is velocity a scalar or vector quantity? 2 can you have a zero velocity but still be moving? 3 give one example of uniform motion and non-uniform motion. 4 what is the difference between speed and velocity? Exit list. Key differences: speed versus velocity. Feature: speed, velocity, quantity, type, scalar, vector, direction not required. Required formula: distance divided by time, displacement divided by time, path follows actual path. Shortest straight path. Lecture note: variable, instantaneous and average velocity. 1. Variable velocity definition: a body has variable velocity if it undergoes unequal displacements in equal intervals of time. It can also vary due to change in speed, magnitude, change in direction, or both. Example: a car moving in city traffic. A person jogging on a curved track. Trick to remember: variable is equal to varying plus velocity, speed or direction keeps changing. 2. Instantaneous velocity definition: it is the velocity of a particle at a specific instant of time. Used when motion is non-uniform, speed direction changes frequently. Formula: V equals numerator cap delta S and numerator over cap delta T, where cap delta S is a very small displacement. Cap delta T is a very small time interval. Graph interpretation: if you draw a tangent to a curve on a displacement tying graph, the slope of the tangent gives instantaneous velocity. V equals cap C cap B over cap A cap C. Trick to remember: instant is equal to 1 moment, tangent slope is equal to instantaneous velocity. Example: speed shown by a speedometer at a specific moment. 3. Average velocity. Picture 67. Definition: it is the total displacement divided by total time taken. Formula: average velocity equals total displacement over total time. Example: a body travels 16 m in first second, 9 m in second, 20 m in third second. Total displacement is equal to 16 plus 9 plus 20 is equal to 45 m. Total time is equal to 3s. Average velocity equals 45 thirds equals 15 movers alternate. Formula: when initial and final velocity known. Average velocity equals numerator u plus v and numerator over 2, where u is equal to initial velocity, v is equal to final velocity. Only valid for uniform acceleration. Important notes: average velocity can be 0 if displacement is 0. E.g. running one full round on a circular track. Average speed is never 0 unless the body didn't move at all. Quick recap table: quantity formula type depends on example variable velocity, not fixed vector displacement and time. Car in traffic instantaneous velocity. V equals s over dt vector at a single moment speedometer reading. Average velocity v sub a vg equals over t vector total displacement and time. Jogging one way on a road. Average velocity all numerator u plus v and numerator over 2 uniform accel. Vector initial and final velocity. Car accelerating uniformly. Classroom tip for teachers: use stopwatch plus tape to measure displacement in timed intervals. Draw a curve on the board and show tangent to explain instantaneous velocity. Create a story. Ravi walks forward, backward, stands still. How will speed and velocity change? Lecture note: acceleration. What is acceleration? Acceleration is the rate of change of velocity with respect to time. It tells us how fast the velocity is increasing or decreasing. Formula for acceleration: acceleration open panna dot close paren equals numerator v minus u end numerator over t, where u is equal to initial velocity, v is equal to final velocity, t is equal to time taken, a is equal to. Acceleration vector quantity has both magnitude and direction. Units of acceleration: psi unit, meter per second square, ms superscript 2, Cbse unit, centimeter per second square, cms superscript 2. Trick to remember: acceleration is equal to how quickly your speed changes. Vu is equal to change in velocity divided by time to get acceleration. Uniform acceleration. Picture 66. A body is said to be in uniform acceleration if its velocity changes by equal amounts in equal time intervals. Example: if a body's speed increases by 10 ms every second, at 1 second 10 ms, at 2 sec 20 ms, at 3 sec 30 ms, then a dot equals numerator 20 minus 10 end numerator over 1 equals 10 superscript base m over s end base squared. Graph explanation: in a velocity versus time graph, a straight line sloping upward is equal to positive acceleration. A straight line sloping downward is equal to negative acceleration. Retardation: a horizontal line is equal to zero acceleration. Uniform velocity. Retardation: deceleration. When velocity decreases with time, acceleration is negative. Example: if speed drops from 40 ms to 10 ms in 3 seconds, a dot equals numerator 10 minus 40 end numerator over 3 equals minus 10 superscript base m over s end base squared. This is called retardation or deceleration. Non-uniform acceleration occurs when velocity doesn't change uniformly with time. Example: speed increases quickly, then slowly, then quickly again. Acceleration is not constant. Example from the textbook: if a body travels with 10 ms at point A, 20 ms at point B, 30 ms at point C, 40 ms at point D, and time taken between each is 1 second. Acceleration at each step: a dot equals numerator 20 minus 10 end numerator over 1 equals 10 superscript base m over s end base squared. A dot equals numerator 30 minus 20 end numerator over 1 equals 10 superscript base m over s end base squared. A dot equals numerator 40 minus 30 end numerator over 1 equals 10 superscript base m over s end base squared. Since the acceleration is the same, it is uniform acceleration. Quick summary table type definition: acceleration value graph shape. Example: uniform acceleration equal velocity change in equal time constant straight sloped line. Car increasing speed steadily. Non-uniform acceleration unequal velocity change in equal time. Varies curved or jagged line vehicle in traffic. Retardation negative. Velocity decreases over time. Negative straight sloped line car slowing down. 0 acceleration velocity is constant. 0 horizontal line cruise control on highway. Teacher tips: use velocity tying graphs to explain concepts visually. Demonstrate using toy car ramps or stopwatches. Ask: if a car goes faster every second, is it accelerating or not? Lecture note: equations of uniformly accelerated motion. These equations describe the relationship between displacement s, velocity u, and v, acceleration a, and time t. When a body moves in a straight line with uniform acceleration. First equation of motion formula V equals plus t, where u is equal to initial velocity, v is equal to final velocity, a is equal to acceleration, t is equal to time taken, meaning this equation gives the final velocity of a body after time t. If it starts with velocity u and moves with constant acceleration a. Example: a bike starts from rest u equals 0 and accelerates at 2 ms superscript 2 for 5 seconds. V equals 0 plus 2 times 5 equals 1. 0 movers. Trick to remember: V is equal to U plus at. Very useful and trusted, easy mnemonic. 2nd equation of motion formula is equals to t plus 1/2 r dot t squared, where s is equal to displacement, u is equal to initial velocity, t is equal to time, a is equal to acceleration, meaning it gives the distance traveled in time t when starting with velocity u and accelerating at a. Example: if a car starts with u equals 5 movers, accelerates at 2 ms superscript 2 for 3 seconds. S equals 5 times 3 plus 1/2 times 2 times 9 equals 1. 5 plus 9 equals 2. 4 m. Trick to remember: s is equal to ut plus half at square. 3rd equation of motion formula v squared equals u squared plus 2as, where v is equal to final velocity, u is equal to initial velocity, a is equal to acceleration, s is equal to displacement, meaning it relates the velocity and displacement directly without using time. Example: if a car starts at 4 ms and covers 20 m with acceleration 2 ms superscript 2, v squared equals 4 squared plus 2 times 2 times 2 0 equals 1. 6 plus 8 0 equals 9. 6 simply s equals square root of 96, almost equal to 9.8 movers. Trick to remember: v square is equal to u square plus 2 as. For displacement in the nth second formula, cap s sub n equals plus over 2 open paren 2n minus 1 close paren, where cap s sub n is equal to displacement in the nth second. Example: a body starts from rest, u is equal to 0 with acceleration 2 ms superscript 2. Find distance traveled in 5th second. Cap s sub 5 equals 0 plus 2 halves open paren 2 times 5 minus 1 close paren equals 1 times 9 equals 9 m. Trick to remember: u plus half a, 2n1 gives the distance in the nth second. Summary table equation formula used when. First equation v equals plus t. Need final velocity. Second equation equals t plus 1/2 r dot t squared. Need displacement with time. Third equation v squared equals u squared plus 2as. Need final velocity without time. Distance in nth second. Cap s sub n equals plus over 2 open paren to n minus 1 close paren. To find distance in specific second, teacher tips ask students to derive equations step by step using average velocity. Use simple real-world examples like cars, falling balls, and racing. Encourage drawing velocity tying graphs to reinforce concepts visually. Lecture note: problem-solving tactics and average velocity in kinematics. Why are sign conventions important? When dealing with vector quantities like displacement, velocity, and acceleration, their direction matters. Hence, we use sign conventions, plus or, to show direction. Convention I: the direction of displacement is taken as positive. All vectors in the same direction are positive, opposite direction is negative. Convention 2: use a Cartesian coordinate system. Origin is at the starting point, and directions are assigned plus or according to the axis. Tip: choose the direction of motion as positive by default unless stated otherwise. Example: average velocity in 3-stage journey. Question: a car starts from rest, u is equal to 0, accelerates uniformly to 40 km per hour, stage 1. Moves at constant speed for a while, stage 2, then retards uniformly to rest, stage 3. Time ratio for the 3 stages is 1:3:1. Find the average velocity. Step-by-step solution. Stage 1: acceleration. Initial velocity u equals 0, final velocity v equals 40 km. Time taken is equal to t. Displacement is equal to s sub 1. S sub 1 equals numerator v plus u and numerator over 2 dot equals numerator 40 plus 0 and numerator over 2 dot equals 20t. Stage 2: constant speed. Speed is equal to v equals 40 km. Time taken is equal to 3t. Displacement is equal to s sub 2 equals v dot equals 40 dot 3t equals 120t. Stage 3: retardation. Initial velocity u equals 40 km, final v equals 0. Time is equal to t. Displacement is equal to s sub 3. S sub 3 equals numerator v plus u and numerator over 2 dot equals numerator 0 plus 40 and numerator over 2 dot equals 20t. Total distance traveled equals sub 1 plus sub 2 plus sub 3 equals 20t plus 120t plus 20t equals 160t. Total time taken t sub t total equals plus 3t plus t equals 5t. Average velocity equals total distance over total time equals 160t over 5t equals 32 km. Tricks to remember: use ratios to divide time easily. For acceleration or retardation, use equals numerator u plus v and numerator over 2 dot. In multi-stage problems, solve each stage separately and then add total distance and time. Teacher tips: emphasize the use of correct sign and direction in vectors. Guide students to solve multi-part motion problems stage by stage. Lecture note: motion under gravity concept overview. When objects move vertically under the influence of Earth's gravity, they experience a constant acceleration called bold cap A bold C bold E bold L bold E bold R bold A bold T bold I bold O bold N bold D bold U bold E bold T bold O bold G bold R bold A bold V bold I bold T bold Y open paren bold J close paren equals 9.8 superscript base M over S N base squared key cases. Enter list 1. Freely falling body dropped from a height 2. Body projected vertically upward. Exit list sign convention tip. Take downward direction as positive g equals plus 9.8 superscript base M over S N base squared. Take upward direction as positive g equals minus 9.8 superscript base M over S N base squared. Final result will be same even if directions are reversed if signs are used consistently. 1 freely falling body initial velocity equals 0. The object is dropped from rest. Equations of motion take equals 0 A dot equals plus G. V equals T equals 1/2 squared V squared equals 2GS. Where V is equal to velocity at any time Ts or h is equal to height fallen in time t. Time of descent from height h, equals square root of 2h over gn square root. Example. An object is dropped from a height of 78.4 m. Equals square root of numerator 2 times 78.4 and numerator over 9.8 and square root equals square root of 16 equals 4 seconds. 2. Vertically projected body thrown upward. Here, the body goes against gravity with initial velocity u slows down, reaches max height, and falls back. Take a dot equals minus g v equals to minus t equals to t minus 1/2 squared. V squared equals to squared minus 2gh at maximum height, final velocity v equals 0. Time to reach maximum height, t sub equals to over g total time of flight. Cap equals to t sub equals to u over g. Example, an object is thrown up at 29.4 ms. T sub equals 29.4 over 9.8 equals 3 simply s. Cap equals 6s. Summary table case equation 1 equation 2 equation 3 time formula. Free fall v equals t equals 1/2 squared. V squared equals 2gs equals square root of 2h over g and square root vertical upward projection v equals to minus t. Equals to t minus 1/2 squared v squared equals to squared minus 2gh. T sub equals to over g total time of flight up and down. Cap equals to u over g. Tricks to remember: up means minus g. Down means plus g. Use v equals 0 at topmost point. Time of ascent is equal to time of descent. Height is maximum when v is equal to 0. Teaching tips for teachers. Enter list.
Bullet.
Drop a ball from a height and time it. Compare with equals 1/2 squared.
Bullet.
Use slow motion videos to show how velocity decreases on the way up and increases on the way down.
Bullet.
Make students sketch velocity tying graphs. Exit list. Lecture note: time of descent and time of flight. Vertical motion. 1 time of descent, TD. When a body is dropped from a height h, the time to reach the ground is called the time of descent. Formula: T sub d equals square root of 2h over g n square root, where h is equal to height from which the object is dropped. G is equal to acceleration due to gravity 2. Time of descent for projected body. When a body is projected vertically upward, it rises to a maximum height and then falls back like a freely falling body. After reaching its highest point, the body behaves like it was dropped from height h. The descent time can also be found using T sub d equals u over g, where u is the initial upward velocity. This proves that time of ascent is equal to time of descent. Trick to remember. Time up is equal to time down for a body projected upward and returning to same level. Descent uses same formula as free fall, just from maximum height. 3 time of flight, TF. Definition: time of flight is the total time the object remains in air after being thrown vertically upward and returning to the same level. Formula: T sub F equals sub up plus sub down equals u over g plus u over g equals 2u over g. Example: a ball is thrown upward with speed equals 20 movers, g equals 10 superscript base m over s n base squared. T sub f equals 2u over g equals numerator 2 times 20 and numerator over 10 equals 4 seconds. Summary table. Term formula meaning time of descent square root of 2h over g n square root time to fall from height h. Time of descent projected u over g time to fall back from max height. Time of ascent u over g time to rise to maximum height. Time of flight 2u over g total time in air up plus down. Final concept wrap up. The moment a ball is thrown upward, it starts decelerating. At maximum height, velocity becomes 0. Then it falls back, accelerating due to gravity. The time to rise is equal to time to fall. Teacher tips. Show slow motion video of an object thrown up and coming back to demonstrate symmetry. Ask students to calculate flight time of different sports actions: cricket ball, basketball shot. Make students derive the formula from the graph or kinematic equations. Lecture note: velocity on reaching the ground, vertical motion concept overview. When a body is dropped from a certain height, it gains velocity as it falls due to the acceleration from gravity. Similarly, when a body is thrown upward, it loses velocity until it reaches the highest point. Case 1: body dropped from height h, initial velocity equals 0. Acceleration a dot equals final velocity v on reaching the ground. Formula used: v squared equals u squared plus 2gh since u equals 0. v equals square root of 2gh. Case 2: body projected upwards to reach height h. Final velocity at max height is equal to 0. Initial velocity equals. Using the same formula, 0 equals u squared minus 2gh implies u equals square root of 2gh. Observation: the speed with which an object must be projected upward to reach height h is equal to the speed with which it hits the ground if dropped from that height. But their directions are opposite, so velocities are not the same, only speeds are. Trick to remember: up or down, to or from a height h, the speed is square root of 2gh. Just change the sign of velocity for direction. Example problem Q: a body is dropped from a height of 45 m. Find the time taken to reach the ground. Given equals 0 equals 10 superscript base m over s n base squared equals 45 m. Solution using = t plus 1/2 squared 45 equals 0 plus 1/2 10 squared implies 45 equals 5t squared implies squared equals 9 implies equals 3 seconds. The body reaches the ground in 3 seconds. Summary table. Motion type formula description falling from height h equals square root of 2gh. Velocity on reaching the ground projected up to height h equals square root of 2gh. Initial velocity needed to reach height. Time to fall from height h equals square root of 2h over g and square root time of descent. Teacher tips: use ball drop experiments from different heights. Ask, what if we throw the same ball up? How fast should we throw to make it reach that height? Reinforce the idea of directional sign in velocity. Lecture note: projectile motion. What is a projectile? A projectile is any object that is thrown or launched into the air and then moves under the influence of gravity, neglecting air resistance. Examples: a mango falling from a tree, a ball projected vertically upward, a ball kicked horizontally from a building. Picture 65, a missile fired from a cannon. Picture 64, path of a projectile. Trajectory: if the object has only vertical motion, path is a straight line. If it has both horizontal and vertical velocity, path becomes a parabola. This curved path is called the trajectory. Types of motion in a projectile. A projectile has two independent motions. Enter list. 1. Horizontal motion, uniform velocity, no acceleration. Exit list. A sub x equals 0 equals to sub x dot. Picture 63. Enter list. 2. Vertical motion, uniformly accelerated motion due to gravity. Exit list. A sub y equals to sub y plus 1/2 squared v sub y equals to sub y plus t. V sub y squared equals to sub y squared plus 2gy. Picture 62. Lecture note: uniform circular motion. What is uniform circular motion? Picture 61. When a body moves in a circular path with a constant speed but the direction of motion keeps changing, it is said to be in uniform circular motion. Key points: speed remains constant. Velocity changes because direction changes continuously. Since velocity changes even if speed is constant, the body experiences an acceleration. This acceleration is called centripetal acceleration. Centripetal acceleration acts towards the center of the circular path, keeps the object moving along the circle. Trick to remember: centripetal is equal to center-seeking acceleration. Real-life examples: a person on a merry-go-round, a car turning around a circular track, Earth revolving around the Sun, an electron moving around the nucleus. Direction of velocity: at every instant, velocity is tangent to the circle as shown in figure 2.14. The arrow representing velocity is always perpendicular to the radius drawn to the point. Tip: at every point on the circle, the object tries to move straight but gets pulled inward. Important terms: term description. Speed constant, does not change. Velocity changes due to changing direction. Acceleration exists, directed towards the center. Centripetal force required towards the center. Centripetal force. Why is acceleration present in uniform circular motion? Acceleration is equal to change in velocity time. Even though speed is the same, direction of velocity changes, so acceleration exists. This keeps the object moving in a circular path instead of moving straight. Quick memory tricks. Centripetal means center seeking. Velocity is tangent, acceleration is radial, towards center. Uniform speed is not equal to uniform velocity in a circle. Teacher tips: use a ball tied to a string and whirl it around to demonstrate centripetal force. Draw arrows showing velocity at different points around a circle. Ask students, why does a car have to steer continuously while turning around a circular track even if moving at constant speed? Would you like me to also prepare a worksheet with simple questions on uniform circular motion? Important terms and formulas. Let a projectile be projected at an angle theta with velocity u. Horizontal velocity u sub x equals to cos theta. Vertical velocity u sub y equals to sin theta. One time of flight, t. Total time the projectile remains in air. Capt equals numerator, 2u sin theta and numerator over g2. Maximum height h. Cap equals numerator u squared sin squared theta and numerator over 2g. 3. Horizontal range r. Total horizontal distance covered. Cap equals numerator u squared sin 2 theta and numerator over g. Range is maximum when theta equals 45 to the ring operator. Horizontal projection from height h. Initial vertical velocity is equal to 0. Initial horizontal velocity is equal to u. Time to fall equals square root of 2h over g and square root. Range cap equals so dot equals a square root of 2h over g and square root. Summary table. Quantity formula depends on time of flight. Cap equals numerator 2u sin theta and numerator over g. U theta g. Maximum height. Cap equals numerator u squared sin squared theta and numerator over 2g u theta g. Range cap equals numerator u squared sin 2 theta and numerator over g u theta g. For horizontal launch, cap equals a square root of 2h over g and square root u h. G. Tips and tricks. Horizontal and vertical motions are independent of each other. Use component method. Resolve velocity into u sub x and u sub y. Always choose downward direction as positive for gravity graphs. Horizontal displacement, straight line, constant velocity. Vertical displacement, curved, accelerated motion. Teacher tips: use a small ball and slide to show parabolic motion in class. Draw motion graphs, height versus time, velocity versus time, vertical. Ask students to calculate range for a given height and velocity. Lecture note: graphical representation of motion along a straight line. What is it about? The motion of an object in a straight line can be understood better by drawing graphs. These graphs help us visualize how an object moves over time. Purpose: To study rectilinear motion in a straight line. To understand how displacement, velocity, and acceleration change with time. Axis convention: x-axis always shows time t, y-axis shows the quantity that changes, displacement s, velocity v, acceleration a. Time is the independent variable s, v are dependent variables, they change with time. Types of graphs in kinematics: 1. Displacement time graph, st graph. What it shows: how far an object has moved over time. Motion type graph: shape uniform motion, straight line, positive slope. Object at rest, horizontal line, no slope, non-uniform motion. Curved line trick: slope of st graph is equal to velocity. To velocity time graph, vt graph. What it shows: how velocity of an object changes with time. Motion type graph: shape uniform, acceleration straight, sloped line uniform, velocity horizontal line. Retardation, deceleration, downward sloping line tricks: slope of vt graph is equal to acceleration. Area under vt graph is equal to displacement 3. Acceleration time graph, at graph. What it shows: how acceleration changes with time. Motion type graph: shape uniform, acceleration horizontal, straight line, variable acceleration irregular or curved. Tricks: area under at graph is equal to change in velocity. Real-life examples: displacement time, a train steadily moving from a station. Velocity time, a car speeding up or slowing down. Acceleration time, a rocket launch showing increasing acceleration. Summary table. Graph type: x-axis, y-axis, slope gives, area gives. St graph: time, displacement, velocity, vt graph. Time, velocity, acceleration, displacement, at graph. Time, acceleration. Change in velocity. Teacher tips: use graph paper or animation tools to draw and explain graph transitions. Ask students to interpret real-life situations from graphs. Let students guess motion types from given graphs for fun. Lecture note: displacement time graphs, st graphs. Why use these graphs? Displacement time st graphs help us understand how position, displacement, of a body changes with time in rectilinear, straight line motion. Axis convention: x-axis, horizontal, time t, y-axis, vertical, displacement, s. Time is the independent quantity. Displacement is the dependent quantity. Case 1: body at rest with zero displacement. Picture 60 graph, horizontal line on the x-axis, s is equal to 0 always, meaning body hasn't moved at all. Trick: flat on x-axis is equal to flat still is equal to not moving. Case 2: body at rest with some displacement. Picture 59 graph, horizontal line parallel to x-axis but above it, meaning body is stationary but not at the origin, has some initial displacement. Trick: constant height from x is equal to body at rest at fixed position. Case 3: uniform motion from origin. Picture 58 graph, straight line starting from origin with constant slope, meaning body moves with uniform velocity, displacement increases equally with time. Trick: straight line from origin is equal to steady motion from 0 point. Case 4 Uniform motion with initial displacement. Picture 57 graph straight line with positive y-intercept, meaning body started from some position and then moved with constant velocity. Trick starts above origin but still straight, moving with steady speed. Case 5 Comparing two objects P and Q. Picture 56 graph two lines from origin with different slopes, meaning both bodies start from the same point but with different velocities. Steeper slope is equal to greater velocity if slope of Q slope of P V sub cap Q greater thumb sub cap P. Slope is equal to velocity v equals displacement over time equals slope of the graph. Summary table. Graph shape motion type notes line on x-axis S is equal to 0. Body at rest, origin no movement at all, horizontal line above x-axis. Body at rest, shifted position, not moving but not at origin. Sloped line from origin, uniform velocity from origin, constant speed 0 initial S. Sloped line from above origin, uniform velocity with initial S. Moving plus already displaced two lines with different slopes, two bodies with different speeds. Steeper line is equal to faster body. Teacher tips: use real-time motion toy car chalk on whiteboard to draw live displacement tying graphs. Ask which graph shows a faster object. Let students match real-world scenarios to graph shapes. Lecture note: displacement tying graphs, part 2, curves, acceleration, retardation. Quick recap of what ST graphs show. Displacement time. ST graphs plot how far an object has moved over time. The slope of an ST graph is equal to velocity. Shape of the graph reveals whether motion is uniform or non-uniform. Case 6 Comparing motion with different slopes. Picture 55 graph two slanted lines R and T starting from different y values, meaning both R and T have uniform motion, straight lines. T has a steeper slope, so T is faster than R. Slope of T, slope of R V sub cap T greater thumb sub cap R. Case 7 Curved graph acceleration. Picture 54 Picture 53 graph ST graph is a curve bending upward, meaning displacement increases faster as time goes on. The object is speeding up. Velocity is increasing. Acceleration curve gets steeper with time. Trick: slope getting steeper is equal to accelerating. Case 8 Curved graph retardation slowing down. Picture 52 graph ST curve bends flattening out as time increases, meaning the slope of the curve is decreasing with time. Velocity is reducing. So the body is slowing down. Retardation slope at Q, slope at P V sub cap Q less thumb sub cap P. Trick: flattening slope is equal to slowing down. Case 9 Negative velocity displacement decreases. Picture 51 graph a straight line sloping down, making an obtuse angle with x-axis, meaning displacement is decreasing with time. Motion is in the opposite direction to displacement. The object is moving back. Slope is negative. Velocity is negative. Trick: line going down is equal to reverse direction instantaneous velocity from curved graph. To find velocity at a specific time on a curve, enter list 1. Draw a tangent at that point. To measure its slope equals displacement over time equals AB over B, where AB is equal to vertical S, BC is equal to horizontal T. Exit list used in case 7 and 8 to analyze acceleration retardation. Summary table of advanced ST graphs. Graph type, motion type. Slope meaning behavior curved upwards, acceleration slope increases, speed increasing. Curved downwards, retardation slope decreases, speed decreasing. Two lines, steeper versus less steep. Comparing speeds, more slope is equal to more speed, T faster than R. Line sloping downward, uniform negative velocity, negative slope, object moving back. Teacher tips: use chalk and string to physically trace curves on the board to show steepening or flattening. Ask students to estimate velocity by comparing the slopes of different segments. Provide real-world analogies: car speeding up, case 7, slowing down, case 8, reversing, case 9. Lecture note: displacement tying graphs, retardation plus opposite direction motion. Recap: what is a displacement tying graph? ST. It shows how far an object moves over time. The slope of the curve at any point is equal to velocity. A curved graph means non-uniform velocity. A decreasing displacement means motion is in the reverse direction. Case 10, retardation in opposite direction. Picture 50. Graph type: a downward bending curve showing decreasing displacement, meaning body is moving opposite to the original direction since displacement decreases. It's also slowing down over time, retardation. Velocity at 2 points. Slope at P is steeper than Q. V sub 1 greater thumb sub 2. Implies the body is retarding, speed decreasing. Trick to remember: curve bends flatter is equal to losing speed, curve goes down is equal to reverse direction. Direction of velocity is opposite to the direction of increasing displacement. Case 11, retardation with initial displacement, still in reverse motion. Picture 49. Graph type: starts from a height, initial displacement, and curves downward, meaning body starts at a non-zero displacement. Displacement decreases over time, object moving backward. Velocity is non-uniform because it's a curve. Slope of tangent at A, slope at B. V sub cap A greater thumb sub cap B. Object is slowing down while reversing. Trick: higher start point is equal to initial position, curve getting flatter downward is equal to reverse plus slowing down. Summary table: case graph, feature, motion type, key concept. 10. Downward curve, slope P, slope Q, retardation in reverse. Body is going back and slowing. 11. Downward curve from height. Non-uniform velocity, reverse retardation with initial displacement. Key concepts for students. Negative slope on ST graph is equal to motion in reverse direction. Decreasing slope is equal to retardation. Tangent slope at any point is equal to instantaneous velocity. Curved graph is equal to non-uniform velocity. Teacher tips: let students sketch these graphs and label slopes at 2 different points. Physically demonstrate using ball rolling up a slope and slowing, then rolling back. Ask students to guess: is this object speeding up, slowing down, or moving back? Lecture note: uses of displacement tying graph. Why learn displacement tying graphs? Displacement time (st) graphs not only show how far a body has moved but also reveal deeper information about its motion, whether it's at rest, moving uniformly, accelerating, or reversing. Top 5 uses of displacement time graphs. 1. Position of the body. At any time you can read of the displacement of the body at any point in time from the graph. Example, if at t is equal to 4 sec s is equal to 20 m, the body is 20 m from the starting point at that time. Trick: follow the graph like a map. Time is the path, displacement is your location. 2. Instantaneous velocity from tangent slope. Draw a tangent to the curve at any point. Its slope gives instantaneous velocity at that moment. Example: steeper tangent is equal to higher velocity, flat tangent is equal to zero velocity. Trick: think of slope as steepness is equal to speediness. 3. Average velocity from overall slope. Draw a straight line between initial and final points on the curve. The slope of this line gives average velocity. Average velocity equals final displacement, initial displacement, over total time. Example: if displacement changes from 0 to 50 m in 5 seconds, average velocity is equal to 10 ms. Trick: slope of full journey is equal to total average speed. 4. Nature of motion. By looking at the shape of the graph you can say whether motion is at rest, flat line, uniform, straight sloped line, accelerated, curve upward, retarded, curve flattening. Example: if graph is getting steeper, acceleration; if graph is flattening, slowing down. Trick: curves talk. Their shapes reveal motion behavior. 5. Parabolic curve for uniform acceleration. For uniformly accelerated motion, the displacement time graph is a parabola. Example: throwing a ball up or freefall motion, st curve is a parabola. Trick: parabola is equal to perfect acceleration. Recap table. Use how to use it. Find position, read y value at given x, time, instantaneous velocity, slope of tangent at any point, average velocity, slope of chord between 2 points. Type of motion. Look at shape, line, curve, up, down. Uniform acceleration identified by a parabolic curve. Teacher tips: use a graphing app or draw simple graphs with students on board. Have students guess the motion type by looking at graph shape. Relate to real-world movement, e.g. elevator motion, car journey. Lecture note: velocity time, VT graphs. Why use VT graphs? Velocity time graphs help us understand how the velocity of a body changes with time. These graphs are useful for analyzing acceleration, rest, and uniform motion. In VT graphs, x-axis is equal to time t, y-axis is equal to velocity v. Case 1: body at rest. Picture 48. Graph type: a straight line on the x-axis. Velocity is equal to 0, meaning the object is not moving. Velocity is 0 for all time. Trick: flat on x-axis is equal to no, motion is equal to at rest. Case 2: body with uniform velocity. Picture 47. Graph type: a horizontal line parallel to x-axis, above or below it, meaning velocity is constant and non-zero, no change in velocity over time. Uniform motion. If it's above x-axis positive velocity, if below x-axis negative velocity, motion in opposite direction. Trick: flat but high is equal to cruising at same speed. Case 3: uniform acceleration from rest. Picture 46, graph type a straight line sloping upward from the origin, meaning velocity increases uniformly from zero. Body started from rest and is speeding up. The slope of the line is equal to acceleration. Acceleration equals change in velocity over time equals slope of Vt graph. Trick: steep slope is equal to rapid speed up. Note: in St graphs, slope is equal to velocity. In Vt graphs, slope is equal to acceleration. Summary table: graph shape, motion type, interpretation, line on x-axis. Rest, no motion, v is equal to 0 always. Horizontal line, v is not equal to 0. Uniform motion, constant velocity, upward sloping line from origin. Uniform acceleration. Speed increasing at constant rate. How to use Vt graphs. Slope is equal to acceleration. Area under the graph is equal to displacement. Displacement equals area under Vt graph. Example: triangle area is equal to 1/2 times base times height. Rectangle area is equal to base times height. Teacher tips: use stopwatches and toy cars to demonstrate velocity changes. Let students match graph shapes to motion types. Reinforce the difference between St and Vt graphs through activities. Lecture note: advanced velocity tying graphs, non-uniform acceleration. Quick recap of Vt graphs. X-axis time t, y-axis velocity v. Slope of the graph is equal to acceleration. Area under the graph is equal to displacement. Case 4: uniform acceleration with initial velocity. Graph type straight line sloping upward starting above the origin. Interpretation: body starts with some initial velocity then accelerates uniformly. Equal increase in velocity over time. Y-intercept is equal to initial velocity. Trick: slope plus starts high is equal to already moving, then speeding up. Case 5: comparing two bodies with different accelerations. Picture 45, graph type two slanted lines starting from different y-intercepts. Interpretation: both have initial velocities p, q, both accelerate uniformly but p's acceleration is greater. Slope of p, slope of q. More slope is equal to more acceleration. Trick: steeper line is equal to faster change is equal to higher acceleration. Case 6: increasing acceleration from rest. Picture 44, graph type curve starting from origin steepening over time. Interpretation: body starts from rest, v is equal to 0 at t is equal to 0. Velocity increases at an increasing rate. Acceleration increases. Slope at point D, point C, a sub 2 greater than sub 1. Trick: upward curve steepening is equal to increasing acceleration. Case 7: decreasing acceleration from rest but not retardation. Picture 43, graph type curve starting from origin but flattening over time. Interpretation: body starts from rest, velocity is increasing but more slowly over time. So acceleration is decreasing, not negative. This is not retardation because speed still increases. Slope at E, slope at F, a sub 1 greater than a sub 2. Trick: curved graph flattening is equal to still speeding up, just slower each second. Summary table case graph type initial velocity acceleration type key feature. 4 sloped line starts above origin yes uniform acceleration from u0. 5 2 sloped lines different slopes yes both uniform both. 1 is accelerating faster 6 curve from origin steepens 0. Increasing acceleration increasing 7 curve from origin flattens 0 decreasing. Not retardation still speeding up. Teacher tips ask students which graph shows greatest acceleration. Look for steepest slope. Challenge them to sketch velocity tying graphs for free fall a ball thrown upward a car accelerating, then cruising. Reinforce slope is equal to acceleration area is equal to displacement lecture note velocity tying graphs retardation cases. What is retardation? Retardation, also called negative acceleration, is when the velocity of a body decreases over time. In VT graphs, retardation appears as a line curve with a negative slope sloping downward from left to right. Axis reminder x-axis, time t y-axis, velocity v. Slope of VT graph, acceleration negative for retardation area under VT graph, displacement. Case 8 uniform retardation straight line down picture 42 graph type straight line making an obtuse angle with x-axis sloping downward interpretation. Body starts with some initial velocity decreases uniformly over time. Constant retardation slope is constant and negative retardation equals minus cap delta V over cap delta T. Trick: steady downward slope is equal to steady slowdown. Think of a brake applied gradually. Case 9 non-uniform retardation decreasing retardation picture 41 graph type curve flattening downward slope decreasing in magnitude interpretation. Velocity is decreasing but the rate of decrease is slowing. Body is slowing down but less and less every second. Slope at GH retardation is decreasing. Trick: curve flattens is equal to soft braking slow down. Case 10 increasing retardation. Picture 40 graph type downward curve that becomes steeper over time interpretation. Velocity decreases quickly as time progresses. Retardation is increasing. Slope at point ij retardation is increasing. Starts at initial velocity ends with zero velocity. Trick: curve steepens is equal to harsh braking fast slowdown. Summary table. Case graph shape acceleration type key feature 8 straight line downward. Uniform retardation constant rate of velocity decrease 9 downward curve flattening. Decreasing retardation body slows more gently over time 10 downward curve steepening. Increasing retardation body slows faster over time. Key learning outcomes. Slope downward is equal to retardation steeper is equal to faster reduction in speed. Flatter is equal to slower reduction in speed. Tangent slope at any point is equal to instantaneous acceleration retardation. Lecture note: acceleration tying graphs AT graphs. What is an AT graph? Picture 39 an acceleration tying graph shows how acceleration changes over time. X-axis time t y-axis acceleration a. Key cases. Case IA is equal to 0 graph a flat line on the time axis. meaning acceleration is zero, body is moving with constant velocity, not accelerating. Trick: zero acceleration is equal to no change in velocity is equal to cruise control. Case: 2a is equal to constant graph, a horizontal line parallel to x-axis but above it. Meaning acceleration remains constant over time, the body is speeding up uniformly. Trick: flat but high is equal to fixed, boost is equal to steady speeding. Uses of acceleration tying graphs. Enter list 1. Find acceleration at any time. Exit list: just read the y value for any point on the graph to get the acceleration. Enter list 2. Find change in velocity VU. Exit list: area under the AT graph is equal to change in velocity. Change in velocity equals area equals r dot time must. Example: if acceleration is equal to 2ms superscript 2 and time is equal to 5s, cap delta v equals r dot time est equals 2 times 5 equals 10 movers. Summary table: graph shape, meaning type of motion, velocity, behavior. Flat on time axis A is equal to 0, constant velocity, velocity unchanged. Flat above time axis A is equal to constant uniform acceleration, velocity increases steadily. Formula reminder: cap delta v equals r dot time must area under AT graph equals velocity change. Teacher tips: reinforce difference between slope and area in AT graphs. Slope is not meaningful. Area is key. Ask: if the graph is a rectangle of height 3ms superscript 2 and width 4s, what's the velocity change? Lecture note: graphical method, motion made easy with VT graph. What is a velocity time VT graph? It shows how velocity of a body changes with time. Slope of VT graph is equal to acceleration, area under the curve is equal to displacement. Used to analyze complete journeys like driving, riding. Examples: graphical area is equal to displacement. To find total displacement, calculate the area under the VT graph by breaking it into triangles and rectangles. Picture 38. Example breakdown graph in Fig 2.41. Picture 37. A person rides a motorcycle with acceleration OD, uniform velocity D, retardation deceleration EC. Let acceleration and retardation last x seconds, and uniform motion lasts 3x seconds. Step-by-step solution. Enter list 1. Break graph into shapes. Exit list: triangle OAD, rectangle AB, triangle BEC. Enter list 2. Use area formulas. Exit list: triangle 1/2 times base time shade, rectangle length times breadth. Enter list 3. Plug in. Exit list: caps equals area open parent cap O cap A cap D plus cap A cap B cap E cap D plus cap B cap E cap C close parent equals 1/2 open parent cap O cap D close parent open parent cap A cap D close parent plus open parent cap D cap E close parent open parent cap A cap B close parent plus 1/2 open parent cap E cap C close parent open parent cap B cap E close parent. With OD is equal to EC is equal to 40 ms, AD is equal to C is equal to XS, D is equal to 3XS. caps equals 1/2 open paren 40 close paren open paren ksha close paren plus open paren 3x close paren open paren 40 close paren plus 1/2 open paren 40 close paren open paren ksha close paren equals 20x plus 120x plus 20x equals 160x m. Enter list 4. Total time is equal to x plus 3x plus x equals 5x. 5. Average velocity exit list. Average velocity equals cap s over cap t equals 160x over 5x equals 32 movers or mover. Understanding motion in parts from Fig 2.42 segment description observation. AB starts with acceleration u is equal to 0 a0. BC uniform motion v is equal to constant CD applies brakes retardation starts. A0 stops completely v is equal to 0 EF. Moves backward with increasing speed v0 a0 negative direction. FG still in opposite direction but slowing retardation in reverse. G stops again v is equal to 0. End of motion formulas recap. Displacement is equal to area under Vt graph acceleration is equal to slope is equal to cap delta V over cap delta T. Average velocity is equal to total displacement over total time. Tricks to remember: area under Vt is equal to total displacement, slope up is equal to acceleration, slope down is equal to retardation below x. Axis is equal to motion in reverse direction. Layout options, text wrapping and positioning available. 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 Stop. No.